Hello, my name is Shuangping Li. I'm from Princeton University. Today I will talk about proof of the contiguity conjecture and log-normal limit for the symmetric perceptron. This is based on joint work with my advisors Emmanuel Abbe at EPFL and Allan at Princeton University. Let's get started with the model. So we consider a matrix G of size m by n, where each entry of G equals to plus or minus 1 with probability a half that are ID distributed. Below, you can see a picture illustration. A green dot indicates that the entry equals to plus 1, and a white dot indicates that the entry equals to minus 1. And we look for a vector x that are of length n, where each entry belongs to plus or minus 1, such that we want the vector x to satisfy a set of inequalities. For any real number kappa, we define the following solution set. So S of G is defined to be the set of all x inside the set, such that the matrix G times our vector x normalized by 1/√n is larger than or equal to kappa entry wisely. So in the picture illustration, this is our matrix, this is our vector. After normalization, we want the resulting vector, we want each entry of it to be larger than or equal to kappa. Okay, so for each of the x in the set, we call it the solution because it satisfies this set of inequalities, and the set of all such x is called the S of G, the solution set. So this is the model, and the reason that people consider such perceptron model is because perceptrons are building blocks for neural network, and it is actually the original motivation for considering such model. And there are three main questions that we consider when talking about perceptron. The first is existence of solutions. More specifically, we look at the regime when m and n goes to infinity with a fixed ratio alpha, and ask for what value of alpha can we find a solution with high probability. So recall that m is sort of the number of rows of the matrix, or in other words, the number of constraints that we have. And n is the dimension we live in. So it's natural to expect that when m is larger, or in other words, alpha is larger, there's more constraints, so it's harder to find a solution. So this question is really asking, so what is the largest value of alpha, such that you can still find a solution with high probability? So that's the first question regarding existence of solutions. And the second question is asking about the structural properties of solution space. So what are some special properties? Are all of the solutions well connected, or do they separate it into different pieces? So structural properties. The third question is regarding efficient algorithms. Can you find polynomial time algorithms that can locate solutions in this solution set? So three questions to consider: existence of solutions, structural properties, and efficient algorithm. Okay, so now let me go through some of the predictions and some of the previous works. So regarding existence of solution, there's this sharp threshold conjecture that predicts that the probability of the existence of solutions undergoes a sharp thresholding phenomenon that jumps from 1 to 0 at some specific value of alpha. And we call this threshold the critical capacity, or alpha C of kappa, which is formally defined as the supermodel of alpha, such that solution exists with high probability as n goes to infinity. So sort of what this sharp threshold conjecture is saying is really, you expect to see that when alpha is below alpha C of kappa, there is expected to see solutions with high probability, whereas when your alpha is above alpha C of kappa, there's no solution with high probability. And the exact prediction of the value of alpha C of kappa is given in this paper by Cross and Medard in 1989. And their prediction is pictured on the left-hand side, where the x-axis is k, or kappa, which is a constant involved in our inequality on the last slide. And the y-axis is alpha, the ratio of m and n. And the yellow region indicates the set phase, where you expect to see solutions with high probability, and the white region is the unset phase, where you don't expect to see solutions. So for a fixed value of kappa, you look at the largest value of alpha such that you're still in the set phase, then this is like the value of alpha C of kappa. And the prediction is actually computed by some of the replica symmetric computation from physics. So this is a predicted picture of what should be happening. You really have a sharp threshold somewhere here, okay? And what is known rigorously for the existence of solutions? I just want to mention this result by Ding and Sun in 2019. This is a very nice result that they're able to provide a lower bound for the capacity threshold that matches the prediction on the last slide. And also this result of Xu in 2019, which where he showed the existence of sharp threshold. So this is a Fredgard type argument that doesn't show the value of where does this threshold lie, but there's this small interval where your probability jumps from 1 to 0. So the existence of a sharp threshold. Okay, so maybe that's a sort of the picture for what is going on for answering the first question, existence of solutions. So what about the second question? Regarding structural property, there is this very interesting phenomenon that are expected to see in the perceptron model called the strong freezing property. What is this? So two solutions are adjacent if they differ in a single coordinate, and a solution is isolated if it has no adjacent solutions. It's easy to understand from the name, it's isolated. So there, like no neighbor of it is solution. And the strong freezing conjecture says that typical solutions are isolated for any alpha between 0 and alpha c of kappa with high probability. This is a regime where you expect to see solutions. So whenever you expect to see solutions, typical solutions are isolated. A very remarkable phenomenon to see. And so some computation was done in a paper by Cross and Murdar in 1989, and the complete this form of conjecture is provided in this paper by Huang and co-authors in 2013. Okay, and so this is a picture illustration of what is going on for the typical solutions. You can see that a dot indicated solution, that they are isolated and are sort of linear distance away from each other. So actually isolated situation. Okay, so that's what we have for the second question. And for the third question, I'll just go very briefly for this section. There's this list of efficient algorithms. So if we pause here for a second and think for a while, you will notice something contradictory happening, in a sense that on the one hand, we showed, we predicted that it is the case that typical solutions are isolated. So when you see something like this, it usually implies certain amount of typical computational hardness because solutions are isolated. But there's also efficient algorithms available. So how to explain this seemingly contradictory phenomenon between the typical isolated solutions, typical computational hardness, and efficient algorithms? And it is actually explained by saying that we should expect to see that algorithms find atypical solutions, and those atypical solutions form rare, well-connected clusters of solutions. So what does it mean? It is true that most of the solutions are isolated, but except aside from those isolated solutions, there's also some rare, well-connected solutions, and it is those rare, well-connected solutions that are found by efficient algorithms. So there's this very nice contrast between typical isolated solutions and those atypical, well-connected solutions. Okay, and some of this was investigated in the paper by Baldassi and co-authors and another work of ours. Okay, so this is just the phenomenon that you sort of expect to see in the perceptron model. So this is a completely picture for answering those three questions: the existence of solutions, structural properties, and efficient algorithms. Okay, so as indicated in the title, so we're going to talk about the symmetric perceptron. So where it's a symmetric. So now let's talk about the symmetric binary perceptron. For the symmetric binary perceptron, we have the same model for the matrix and vector. It's just we look at a symmetrized version of the inequalities. We require the matrix G times the vector X. Absolute value of that normalized by 1 over root n is less than or equal to kappa. So compared to before, we add in this pair of absolute value and we reverse the sign of the inequality. We want each entry of this to be less than or equal to kappa. That's the symmetric binary perceptron. And why do we consider such symmetric binary perceptron? So this model is expected to be more tractable to work with compared to the original perceptron model, and similar properties are expected to hold. This includes the sharp thresholding phenomenon, the strong freezing phenomenon for solution space, and the existence of this rare, well-connected cluster of solutions. So I want to say that this symmetric binary perceptron was originally introduced by Abbe and co-authors in this paper, and some of the preliminary first and second moment computation was done there. And so according to the computation, you can see that alpha C of kappa actually equals to log 2 plus alpha log of p kappa, where this p kappa is some explicit probability that depends on kappa. Okay. So what are our results in this symmetric binary perceptron model? We showed that for any kappa larger than 0 and alpha between 0 and alpha C of kappa, if we let Z of G to be the number of solutions, then when n goes to infinity, the number of solutions normalized by its expectation converging distribution to a log normal limit, where this beta depends explicitly on alpha and kappa. So so sort of we're able to, in the regime where you expect to see solutions, we're able to characterize how the fluctuation of the number of solutions around its mean. So that's the first, the Lognormal limit theorem that we have. And the theorem have several important consequences. So firstly, it allows us to settle the sharp threshold conjecture and the strong freezing conjecture. And more importantly, it also allows us to show a very strong connection between the random model and the planted model called the contiguity property, as I will talk in a second what it is. So our results, so the first step of our result is showed this log normal distribution for the number of solutions, and it implies the following three results on sharp threshold, contiguity, and strong freezing. So I want to mention a recent work of Perkins and Xu, where they adopt a different approach of ours, but they're also able to show the sharp threshold and strong freezing under a numerical hypothesis. And they're able to, describe the number of solutions up to this level. Here, compared to theirs, our description is a more detailed description that to sort of completely characterize the distribution of the number of solutions. Okay, so now I will go into details of those three results on sharp threshold, contiguity, and strong freezing. So the sharp, sharp threshold phenomenon, as I said before, when alpha is larger than alpha C of kappa, there's no solution with high probability. And when alpha is between 0 and alpha C of kappa, there's a solution with high probability. So that's sharp thresholding. And what about contiguity? So let me first introduce what is a planted model. So as the name indicates, so you want to first plant a solution and then construct your matrix, okay? So we first choose X uniformly at random from this space, vector of length n, where each entry belongs plus minus 1. First choose an solution uniformly at random, and then choose your matrix G, condition on X is one of the solution. Condition on X belongs to this set S of G. So choose an X, and then condition on G, condition on X is a solution of G, choose your G. Then we define P star to be the law of G. So that's the planted model. So the original model or the random model is just, you just directly choose your random matrix G. And the planted model is you go first from a planted solution and then go to your matrix. So to understand this, so actually P star and P are connected by this random Nichols derivative, that the derivative actually equals to the number of solutions normalized by its expectation. So this is sort of how they're related. And what we showed for the contiguity and what is contiguity. So for any kappa larger than 0 and alpha between 0 and alpha C of kappa, we showed that P and P star are mutually contiguous, meaning that for any sequence of events an, P of an goes to 0 if and only if P star of an goes to 0. So what does this say? So if you can find an event that happens with high probability on the one side, also happens with high probability on the other side. So this is a very strong connection between the original model and the planted model, because a lot of the cases, things are easier to show in the planted side. For example, the strong phrasing property that we will see in a second. And if we have this strong phrasing, say in the planted model, then with contiguity, you're able to translate this result back to the original model. And this is like the result that we want to see. So it's really like build a bridge between the random model and the planted model, and are able to translate results, to the other side. So it's a very ideal, result that one might want to have. And so because of this relation, because we sort of characterize the number of solutions normalized by expectation, characterize the distribution of this term on the right-hand side. So that's how we get contiguity from the log-normal limit result we had at the beginning. So that this is like a consequence of the previous result. Okay, and another consequence that we have is this strong phrasing result, that indeed typical solutions are isolated for any alpha between 0 and alpha c of kappa with high probability. So the three results, again, sharp threshold, contiguity, and strong phrasing. So now let me briefly go through the proof and some of the key proof ideas. So a direct first and second moment computation give us the following, that the second moment divided by first moment square converge to a constant larger than 1. So if this constant is 1, then we're good to go, because then we showed that sort of the number of solutions is concentrated around this expectation. But in reality, this is not the case. We have a constant larger than 1. So how to account for this additional variance? We adopt this method called small graph conditioning method, which is originally introduced by Robinson and Werman and Jason. And the method works by explaining the additional variance through the effect that the small cycles in the graph have on the partition function. What does that mean? So we sort of want to show that this normalized number of solution roughly equals to exponential of y, where y is some random variable that equals, some weighted sums of cycles. And so you want to sort of explain the additional variance, of this number of solution through this cycles. And of course, the original smart graph conditioning method is on graphs, but we have like no graphs in the perceptron model. But we were able to come up with like a dense analog of the small graph conditioning technique. And we're able to find this form of a generalized cycle count. So this really equals to some weighted sum of products of entries in the matrix, where this entry sort of form a cycle, in your matrix. Sum over all of those such product, take a weighted sum of those, and we're able to show that indeed the number of solutions normalized by its expectation roughly equals to exponential of y, where y is this weighted generalized cycle count. And by characterizing the distribution of y, and by showing this convergence, we're able to get the log normal limit result that we have. Okay, so let me just go through very briefly how did we come up with this form of the cycle CK. So if we, instead of looking at M constraints, if we just look at the first constraint, then it is the same as saying, absolute value of sum of the sum is less than a number. And, condition on this doesn't change the marginal distribution of entries of Ux, but what it changes, it makes entries of U vectors slightly correlated with each other. And we can do a more detailed computation and say how large is this correlation. And the correlation, the probability distribution is actually proportional to this form. And if you assume that the effects of the rows were multiplicative, then we might expect to see that the probability distribution is proportional to this form. And this looks very similar to the interaction terms in the Sherrington-Kirkpatrick model. And we can use a similar expansion there and write the sums out. And this helps us to come up with this form of the generalized cycle count. So that's the rough proof idea. Thank you very much.